Between the galaxies, there is something that every map of the universe underrepresents. Astronomers confirmed it through X-ray telescopes and quasar light. The space you assume is empty holds more ordinary matter than all the stars and galaxies combined. It reaches temperatures of tens of millions of degrees. It carries magnetic fields. It launches stars at millions of miles per hour. And, until very recently, most of it was invisible to us. We are going to move through that space together. We will cross a void 330 million light-years wide, where almost nothing exists, track a star being hurled out of its galaxy at unimaginable speed, and find where the universe keeps most of its missing matter hidden in superheated filaments, too faint for most telescopes to catch. If you find yourself wanting more of this kind of journey, subscribing helps us keep going deeper. The space between galaxies has been hiding the majority of the universe's story. We are just now learning to read it. Prepare yourselves. We begin. Here is a fact that reframes the entire picture of the universe in one sentence. Everything you have ever seen in images of space, every galaxy, every glowing nebula, every star cluster, accounts for a small fraction of the ordinary matter that actually exists. The majority of it is somewhere else. And for most of modern astronomy's history, we had no idea where. When astronomers mapped the universe's large-scale structure, they could account for the matter inside galaxies. They could measure stars, gas clouds, and dust. But when they added it all up and compared it to what the physics of the early universe predicted should exist, a massive portion was simply absent, gone, undetected. This became one of cosmology's most pressing problems, known as the missing baryon problem. Baryons are the particles that make up ordinary matter, protons, neutrons, everything you can touch or see, and more than half of them were unaccounted for. The leading theory, building for decades, was that the missing matter never disappeared. It hid, spread thin across the enormous spaces between galaxies, too diffuse and too faint for most instruments to catch. Picture it like this. Imagine emptying an ocean into a space the size of a continent. The water is still there. You just cannot see it as a body of water anymore. Confirmation came through multiple approaches. One of the most powerful involved quasars, extraordinarily bright cores of distant galaxies powered by supermassive black holes. When quasar light travels across billions of light-years toward us, it passes through whatever lies in between. Scientists found that specific wavelengths of that light were being absorbed along the way. The absorbing material was gas, intergalactic gas, spread across filaments connecting galaxy clusters across the cosmos. X-ray observatories added another layer of confirmation. This intergalactic gas is superheated to temperatures between 100,000 and 10 million degrees. At those temperatures, it glows faintly in X-ray wavelengths, invisible to the naked eye and to most optical telescopes, but detectable to instruments designed for high-energy observation. In 2017, two independent research teams announced they had directly detected the filaments of this warm, hot intergalactic material, connecting pairs of galaxy clusters. One team used data from a European Space Agency satellite. Another used a different method, stacking signals from many filament regions to boost detection. Both arrived at the same conclusion. The missing matter was there all along, stretched across the skeleton of the universe in threads of superheated gas between the clusters. The scale is difficult to picture. These filaments are not thin wisps. They span tens of millions of light-years. They carry mass comparable to the galaxy clusters they connect, and they exist in the spaces we once called empty. This matters because the missing baryon problem was a foundational gap in our understanding. If we could not locate ordinary matter, the kind we are made of, the kind we understand, then our accounting of the universe was fundamentally broken. The filament detections did not close every question, but they confirmed that the cosmic web is real, that it is massive, and that the emptiness between galaxies is a deliberate illusion created by the limits of our instruments. The universe is mostly located in the spaces between things, and the nature of those spaces is stranger and more active than the word empty ever suggested. But the temperature of intergalactic gas and the location of missing matter are only the surface of what the between-galaxy environment contains. Something far more structured organizes all of it, and that structure was mapped decades ago. Zoom out far enough from any galaxy, and it disappears into a thread. Zoom out farther, and that thread connects to other threads, forming a vast branching network that covers the entire observable universe. Astronomers call it the cosmic web, and it is the largest confirmed structure in existence. The cosmic web has three main components. Filaments are the long, thread-like bridges connecting dense regions. Sheets are the flatter walls where filaments intersect, and nodes are the densest points where multiple filaments meet. Those nodes are where the largest galaxy clusters sit. Between all of it are voids, enormous empty regions where matter is scarce and galaxies are rare. This structure was predicted before it was observed. In the 1980s, computer simulations of how gravity pulls matter together over cosmic time consistently produced the same web-like pattern. When large galaxy surveys began mapping millions of galaxies across hundreds of millions of light-years, the web appeared exactly as predicted. The match between simulation and observation is one of the strongest confirmations in modern cosmology. The driving force behind the cosmic web is gravity, working across billions of years. In the early universe, matter was distributed almost uniformly, but with tiny quantum fluctuations, microscopic differences in density. Gravity amplified those differences. Slightly denser regions pulled in surrounding matter. That matter collapsed into filaments. Filaments drained into nodes, and the regions that started slightly less dense emptied out even further, becoming voids. The result is a universe organized at every large scale by this web pattern. Every massive galaxy cluster sits at an intersection point. Every filament carries gas, dark matter, and occasionally entire galaxies flowing toward those dense hubs. The web is dynamic. It is still evolving. Matter is still moving along filaments toward clusters right now. The Sloan Digital Sky Survey produced some of the clearest observational evidence for the web. By mapping the positions of more than 1 million galaxies, astronomers assembled a three-dimensional picture of the universe's structure out to several billion light-years. The result looked nearly identical to the outputs of simulations. Filaments, walls, voids, nodes, all present, all matching the theoretical framework built decades earlier. What makes the cosmic web alarming in scale is the proportion of space it assigns to emptiness. Voids occupy roughly 80% of the universe's total volume. The filaments and nodes, where essentially all visible matter and light originates, occupy the remaining 20%. Most of the universe, by volume, is void space. Dark matter is the invisible scaffolding underneath all of it. Ordinary gas and galaxies trace the web, but the gravitational architecture holding the web in its shape comes from dark matter. The filaments we see in ordinary matter are sitting inside much larger, dark matter structures that we can only infer through gravitational effects. Mapping the cosmic web has also given astronomers a tool. The web's pattern encodes information about how the universe has expanded over time, and subtle variations in its geometry help measure dark energy. Every large galaxy survey being built today is designed in part to trace the web with higher precision, going farther back in time. The structure is clear. The mechanism is understood in broad terms, and yet the web produces phenomena inside its filaments and voids that standard models still struggle to fully explain. One of those phenomena involves detecting the web itself through light, and the method astronomers use reveals something deeply strange about the nature of intergalactic space. A quasar located billions of light-years away is blazing with light equivalent to trillions of stars. That light travels toward us across the intergalactic medium for billions of years. By the time it arrives, it has been altered by everything it passed through, and astronomers have learned to read those alterations like a fingerprint of the universe's hidden matter. The technique is called the Lyman alpha forest. When hydrogen gas absorbs light, it does so at a very specific wavelength. As quasar light travels through intergalactic hydrogen clouds at different distances from us, each cloud absorbs a slightly different wavelength due to the expansion of the universe, stretching the light over time. The result is a spectrum of the quasar's light peppered with hundreds or thousands of absorption lines, a dense forest of dips and gaps, each one marking a cloud of gas the light passed through. Every line in that forest is a real detection of real matter. Astronomers can measure each line's depth, position, and width. The depth tells how much gas was in the cloud. The position tells the distance. The pattern across the whole spectrum maps the distribution of intergalactic hydrogen along that line of sight across billions of light years. This is one of the most powerful tools in observational cosmology. The Lyman alpha forest has been used to trace the large-scale structure of the universe, measure how fast it has expanded at different periods in history, and search for the signatures of the warm, hot intergalactic filaments predicted by theory. When astronomers look at thousands of quasar spectra, they can statistically reconstruct what the intergalactic medium looks like across enormous cosmic distances. The picture that emerges confirms what simulations predicted. Gas is clustered along filaments. Voids show far fewer absorption lines. Dense regions near galaxy clusters show heavy absorption. The forest is a shadow map of the cosmic web, written in the wavelengths of absorbed light. There is a complication, and it matters. The Lyman alpha forest traces neutral hydrogen well, but the warm, hot intergalactic medium, the superheated filaments where the missing baryons reside, is so hot that its hydrogen is almost completely ionized. Ionized gas does not absorb light in the same way, so the hottest, most massive filaments were partly invisible even to this technique. That is why detecting them required X-ray observations and other methods working together. When scientists cross-reference the Lyman alpha forest data with X-ray maps and with the positions of known galaxy clusters, a coherent structure emerges. The filaments connect the clusters. The absorption lines trace the cooler edges of those filaments. The X-ray glow comes from the hottest cores. Together, they confirm the same web-like architecture from multiple independent directions. The Lyman alpha forest also carries information about reionization, the period in cosmic history when the universe went from opaque to transparent. Beyond a certain distance in the quasar spectra, the absorption becomes nearly total. The light is almost completely absorbed by neutral hydrogen that had not yet been ionized. That transition point marks when the universe was roughly 1 billion years old, and the forest goes dark before it. Every quasar spectrum is a record of the universe's entire history along a single line of sight. Thousands of those records, combined, tell us where the matter is, where it has been, and how the web has evolved. And what those records show, when examined at extreme energies, is something the standard model of the cosmos still has no complete answer for. The space between galaxies feels, intuitively, like the coldest place imaginable. Remove the stars, remove the gas clouds, remove everything you associate with heat, and what remains should be close to absolute zero. The actual measurement tells a different story entirely. The intergalactic medium is hot. In many regions, extraordinarily hot. Confirmed measurements from X-ray satellites show that gas in galaxy cluster environments and along filaments reaches temperatures between 1 million and 100 million degrees. The filaments of the warm, hot intergalactic medium sit in the range of 100,000 to 10 million degrees. These are temperatures that exceed the surface of most stars, sustained across regions spanning millions of light years. How does a place with so little matter reach those temperatures? The answer is gravity and scale. As the universe evolved and matter fell into the gravitational wells of large-scale structure, it did not settle gently. Gas falling into filaments and clusters at high speed collided with other gas and shocked. The collision converted kinetic energy into heat. The larger the structure, the more violent the infall, and the hotter the resulting gas. This process, called shock heating, operates at scales that dwarf anything in a solar system. When matter streams along a cosmic filament and hits a denser region, The collision front moves at hundreds of miles per second. The energy deposited into the gas is enormous, and the gas has almost no way to cool efficiently because it is so diffuse, so the heat remains. For billions of years, confirmation of these temperatures comes primarily from X-ray observatories. The European Space Agency's XMM Newton satellite and NASA's Chandra X-ray Observatory have both mapped hot gas in and around galaxy clusters at high precision. The temperatures measured are consistent with what gravity-driven shock heating predicts. The measurements match across independent missions using different instruments. The hottest gas concentrates in galaxy cluster cores, where the gravitational well is deepest and the gas density is highest. But even in the filaments between clusters, where gas density drops dramatically, temperatures stay elevated. The gas there has been shock heated by the same large-scale infall and cannot radiate that heat away fast enough to cool. There is another heat source layered on top. Quasars and the active cores of galaxies pump enormous amounts of energy into their surroundings. This energy, in the form of radiation and jets of charged particles, heats surrounding gas and drives it outward. Some of that energy escapes into intergalactic space. How much it contributes to heating the intergalactic medium overall is still an active area of research, and estimates vary between scientific teams. What we can say with confidence is this: the space between galaxies is threaded with gas hot enough to emit X-rays. It is hot enough to be measured across cosmic distances, and it holds the majority of the ordinary matter in the observable universe, baking at temperatures that would vaporize anything we know. This raises an immediate question about the particles streaming through that environment. The intergalactic medium is a medium in the physical sense, a material that things move through. Radiation moves through it, and something else moves through it, arriving at Earth with energies that push against the boundaries of what physics can comfortably explain. For decades, one of the clearest predictions of cosmology was also one of its deepest embarrassments. The physics of the early universe, specifically the process by which light elements formed in the first minutes after the Big Bang, predicted with precision how much ordinary matter the universe should contain. Measurements of the cosmic microwave background confirmed that number independently, and then astronomers went looking for all that matter and found only about half of it. The other half was missing, confirmed absent from observations of galaxies, galaxy clusters, and the diffuse gas already detected at the time. This gap persisted from the 1990s through the 2000s and into the 2010s. It was a known, documented problem in the standard cosmological model, not a fringe concern, but a mainstream unresolved issue discussed openly in the scientific literature. The leading hypothesis was that the missing matter existed in the warm, hot, intergalactic medium, the superheated filaments connecting galaxy clusters. This gas would be too diffuse and too hot to emit much visible light, and too spread out to concentrate enough signal for easy detection. Detecting it directly required either finding it in X-ray emission, which demanded long telescope exposures in exactly the right directions, or detecting its faint imprint on other signals. The breakthrough came from two independent teams publishing in 2017 and 2019. One team, led by researchers at the University of Edinburgh, used a technique that involved stacking signals from the cosmic microwave background at the locations of known galaxy pairs. When hot gas sits between two galaxy clusters, it leaves a faint imprint on the microwave background as photons pass through it. By combining data from millions of galaxy pair positions, the team extracted a statistical detection of the gas in the filaments between them. The signal was faint but consistent. A second team used X-ray data from the XMM Newton satellite, targeting a known filament between two galaxy clusters called Abell 453 and Abell 459. They detected X-ray emission along the expected filament position, consistent with hot gas at the temperatures the warm-hot intergalactic medium theory predicted. Both detections pointed to the same conclusion. The missing baryons were real, they were in the filaments, and the cosmological predictions were correct. The matter was never lost. It was beyond our instruments' reach. The confirmed mass in these filaments is substantial. Estimates suggest the warm, hot intergalactic medium holds roughly as much mass as all the matter inside galaxies. Every thread connecting two galaxy clusters is a reservoir of hot gas with a total mass comparable to entire clusters themselves, spread across tens of millions of light years. Finding the missing baryons did not close every question in cosmology. It confirmed a prediction and resolved a specific gap. But the filaments themselves, their exact temperatures, their magnetic properties, their role in galaxy evolution remain active research targets. The next generation of X-ray telescopes, including the proposed Athena mission from the European Space Agency, is designed in part to map those filaments in detail. The missing matter found its address, and the address turns out to be one of the most extreme environments in the observable universe. But matter in those filaments does not just sit still. Some of it moves. Some of it moves very fast. And some of what moves through intergalactic space carries energies that challenge our understanding of physics itself. Something arrives at Earth every second from the depths of intergalactic space. It passes through the atmosphere, occasionally hits a detector, and leaves behind a signature that scientists have been studying for over a century. Cosmic rays are not rays at all. They are particles, protons, atomic nuclei, occasionally electrons moving at extraordinary speed. Most come from within our own galaxy, but the highest energy ones come from somewhere far outside it, and tracking down their origin has become one of the central puzzles of modern astrophysics. The scale of the energy involved is difficult to picture in familiar terms. The most energetic cosmic rays ever detected carry kinetic energy comparable to a professionally thrown baseball packed into a single subatomic particle, a particle smaller than an atom, moving with the energy of a thrown ball. The physics required to accelerate anything to that speed across intergalactic distances involves conditions that are extreme, even by the standards of the universe's most violent events. The Pierre Auger Observatory in Argentina is the largest cosmic ray detector ever built, covering an area of roughly 3,000 square miles of the Pampas, using a network of water tanks and telescopes designed to catch the cascades of secondary particles that high-energy cosmic rays produce when they hit the atmosphere. Auger has been collecting data since 2004, and the picture it reveals is complicated. At lower energies, cosmic rays arrive from all directions roughly equally, consistent with them scattering within our galaxy's magnetic field over long distances. At the highest energies, a slight clustering appears. The arrival directions of the most energetic particles show a weak but statistically significant preference for certain regions of the sky, regions that contain large numbers of nearby galaxies outside our own. One confirmed feature is the GZK limit, named after the physicists who predicted it in 1966. A particle above a certain energy threshold traveling through intergalactic space will interact with the photons of the cosmic microwave background, losing energy over distance. The prediction is that ultra-high energy cosmic rays from more than a few 100 million light-years away should arrive depleted below that energy threshold. Auger data shows a cutoff in the energy spectrum consistent with this prediction, confirming that at least some of the highest energy particles are coming from within a few 100 million light-years. Identifying the exact sources remains unresolved. Active galactic nuclei, which are the violently energetic cores of certain galaxies powered by accreting supermassive black holes, are leading candidates. Starburst galaxies, which are undergoing intense periods of star formation and stellar explosions, are another candidate. The Auger collaboration published a result in 2017 showing a correlation between the arrival directions of the highest energy cosmic rays and the positions of nearby starburst galaxies, but the correlation is not definitive. What we know for certain is this: particles are being accelerated somewhere in the universe to energies that require magnetic fields, shock fronts, or conditions at the boundaries of the known. They cross intergalactic space, passing through the superheated filaments, threading through the cosmic web and arrive here carrying information about the environment they traveled through. And as those particles travel, they are not alone in the void. Something else threads the intergalactic medium alongside them, far more subtle, and its origin is a genuine open question in cosmology. The space between galaxies carries a magnetic field. This is confirmed by observation. It is weak, far weaker than a refrigerator magnet, weaker than Earth's magnetic field by many orders of magnitude. But it is real, it is measurable, and its presence raises a question that cosmology has struggled to answer for decades. Where did it come from? Magnetic fields need to be generated. On Earth, they come from the motion of conducting fluid in our planet's core. In stars, they arise from turbulent, conducting plasma. In galaxies, the mechanism involves rotation and the amplification of seed fields by moving charged particles over billions of years. But in the voids between galaxies, there is almost nothing to drive those processes. The gas density is incredibly low. Large-scale rotation does not exist in the same way, and yet the magnetic field is there. Detection comes from a technique called Faraday rotation. When polarized radio waves, radio light with a specific orientation, travel through a magnetized plasma, the orientation of that polarization rotates. The amount of rotation depends on the strength and direction of the magnetic field along the path and the density of electrons in the medium. By measuring how much the polarization of light from distant radio sources has rotated by the time it reaches us, astronomers can infer the magnetic properties of everything the light passed through. Measurements using this method have detected intergalactic magnetic fields with strengths in the range of 1/10 to 1/1,000,000,000 of a single Gauss. Extraordinarily weak, but coherent across millions of light years, the evidence has accumulated over years of radio telescope observations and was significantly strengthened by data from the LOFAR radio telescope array in Europe, which operates at low frequencies, particularly sensitive to Faraday rotation from diffuse intergalactic plasma. The origin debate splits broadly into two camps. One holds that the fields were seeded early in cosmic history, possibly during the period just after the Big Bang or during the epoch of reionization, and then stretched and thinned as the universe expanded. Some proposals place the seed field generation even earlier, during cosmic inflation. If this is correct, intergalactic magnetic fields are a fossil signal from the earliest moments of the universe, preserved in the void for over 13 billion years. The other camp argues the fields were produced later by astrophysical processes. Galaxies and quasars eject magnetized material into their surroundings. Supernova-driven winds carry magnetized plasma outward. Over time, these outflows could have seeded and spread magnetic fields into the intergalactic medium. On this view, the fields are pollution from galaxies rather than a relic of cosmic origins. Distinguishing between these two scenarios has proven difficult. The fields are so weak that measuring them requires precision at the edge of current technology. Future instruments, particularly the Square Kilometre Array under construction in South Africa and Australia, are expected to map intergalactic magnetic fields across vast volumes of the sky, finally giving astronomers the statistical data needed to trace where the fields originated and how they are distributed. What makes this scientifically significant is the implication for structure formation. Magnetic fields, even weak ones, influence how gas moves. They can affect how matter falls into filaments, how gas cools, and how cosmic rays propagate through the intergalactic medium. A field that exists everywhere in the void is shaping the large-scale environment in ways that are still being quantified. And inside that magnetized void, there are objects drifting that have no right to be there at all. The galaxy ends. The stars thin out, and then, far beyond the last edge of any galaxy, something appears that should be nowhere near this deep in intergalactic space. A star, burning alone, tens of millions of light years from the nearest galaxy, with no cluster, no companion, no home. These are intergalactic stars, and they are real. Astronomers first identified them in the 1990s in the Virgo galaxy cluster, detecting a diffuse glow of starlight between the member galaxies that could only be explained by a population of stars distributed throughout the intracluster space. Later studies, using the Hubble Space Telescope, resolved individual stars in nearby galaxy clusters and confirmed their existence directly. The estimated number of stars living outside galaxies in galaxy cluster environments runs into the trillions. In the densest galaxy clusters, intergalactic stars can account for between 10 and 50% of all the stars in the cluster. That is a staggering proportion. Half the stars in some of the universe's densest environments are homeless, drifting through cluster space rather than bound to any galaxy. The combined light from these stars gives clusters a faint, extended glow called the intracluster light, which has been measured and mapped by multiple space telescopes. The mechanism that produces them is violent. When galaxies collide or interact gravitationally inside a cluster, tidal forces tear stars away from their parent galaxies and scatter them into the broader cluster environment. Galaxy clusters are dynamic, collision-prone environments. Over billions of years of interactions, the gradual stripping of stars from galaxies builds up the intergalactic stellar population one tidal encounter at a time. A separate but related process involves the dynamical friction of smaller galaxies moving through the dense cluster environment. As a smaller galaxy falls into a cluster, its outer stars experience weaker gravitational binding and are more easily stripped. The galaxy loses its outer envelope. Over multiple passages, it can be reduced to a compact remnant while contributing enormous numbers of stars to the intergalactic population. Some intergalactic stars are not simply drifting, they were ejected at high velocity. The gravitational influence of two closely interacting supermassive black holes at the centers of merging galaxies can slingshot individual stars outward at speeds far exceeding the galaxy's escape velocity. These stars leave their host galaxy permanently and travel through intergalactic space as solitary travelers. Given the age of the universe, some may have been traveling for billions of years, so far from any galaxy that they will never return. The intracluster light has become a research tool in its own right. Because intergalactic stars trace the gravitational history of a cluster, they follow the mass, including dark matter. Mapping the distribution of intracluster light gives astronomers a proxy for the dark matter distribution. Observations from the James Webb Space Telescope have produced some of the deepest maps of intracluster light ever obtained, revealing complex substructures that record past merger events like rings left by stones dropped in water. These stars live their entire lives in the void between galaxies, fusing hydrogen into helium in a place that has almost no neighbors, no galaxy backdrop, no spiral arm overhead. Their sky, if you could stand on a planet orbiting one of them, would be darker than anything we know, just a few distant galaxy smudges, where our sky has hundreds of billions of stars. But stars are not the only things being ejected into intergalactic space. Some of what gets thrown out is far more extreme. In 1988, a theoretical paper predicted something that sounded almost impossible. A star, moving fast enough to escape the gravitational pull of an entire galaxy, launched by the gravitational interaction between a binary star system and the supermassive black hole at the galaxy's center. The prediction was specific enough to test, and 17 years later, astronomers found the first confirmed example. That star, discovered in 2005, was moving at roughly 1.5 million miles per hour relative to the center of our galaxy, far above the escape velocity needed to leave the Milky Way permanently. It was a class of object no one had catalogued before, a hypervelocity star. Since then, dozens have been confirmed, and the population almost certainly extends into the hundreds or thousands when accounting for the full sky. The mechanism behind most confirmed hypervelocity stars is called the Hill's mechanism, named after the researcher who first described it in detail. A binary star system, two stars orbiting each other, wanders too close to the supermassive black hole at the galaxy's center. The black hole's gravity disrupts the binary. One star gets captured into a tight orbit around the black hole. The other gets flung outward, gaining the energy released from the orbital breakup. The The speeds achievable through this process can reach several million miles per hour. The supermassive black hole at our galaxy's center, called Sagittarius A star, has a mass roughly 4 million times that of a typical star like our own. Its tidal gravity is extreme enough to tear apart binary stars that pass within a certain distance. Every such encounter is a potential launch event, throwing a star outward at extreme speed. Observations from the European Space Agency's Gaia satellite, which has measured the positions and velocities of over 1 billion stars in our galaxy with extraordinary precision, have helped identify hypervelocity candidates by flagging objects moving on trajectories that trace back to the galactic center. The Gaia data has also revealed some high-velocity stars whose origin traces to other locations, suggesting additional ejection mechanisms beyond the Hill's process may exist. Some hypervelocity stars are on trajectories that will carry them out of our galaxy entirely within a few tens of millions of years. Once outside, they join the broader population of intergalactic travelers, moving through the void at speeds far above any remaining gravitational pull. Their trajectories through intergalactic space are essentially straight lines over cosmological time. A subset of particularly fast runaway stars may receive their velocity not from the galactic center but from supernova explosions in binary systems. When one star in a binary explodes as a supernova, the companion can be released at high speed, freed from the gravitational bond by the sudden loss of mass in the system. These are distinct from Hill's mechanism stars and have different velocity distributions and trajectories, but some can still reach speeds sufficient for galactic escape. The detection of hypervelocity stars has practical value beyond their intrinsic interest. Their trajectories encode information about the galactic potential, the combined gravitational influence of all matter in the galaxy, including dark matter. By tracking where they came from and how their paths curve, astronomers can map the invisible mass through which they have traveled. A star moving at millions of miles per hour through intergalactic space, carrying fossil information about the gravitational landscape it left behind. The universe is constantly launching probes, and we are just beginning to read what those probes carry. The ejection of individual stars at extreme speeds is striking, but it is a small-scale version of a process that can happen to entire black holes. A supermassive black hole containing billions of times the mass of a typical star, torn from the center of its galaxy and sent drifting through intergalactic space. This possibility sits within the range of what current physics permits, and in 2023, a research team announced they may have found one. The candidate was identified in data from the Hubble Space Telescope. Astronomers noticed a narrow streak of intense star formation extending from a galaxy, stretching outward into intergalactic space for roughly 200,000 light-years. The streak contained young, hot, blue stars arranged in a near-perfect line. Lines of triggered star formation do not appear spontaneously. Something caused the gas along that line to compress and form stars all at once, in sequence. The leading explanation, put forward by the research team, is that a massive black hole was ejected from its galaxy and traveled outward through the surrounding gas, compressing material as it moved and leaving behind a trail of newly formed stars in its wake. The proposed mass of the candidate object is enormous, potentially tens of millions of times the mass of a typical star. If confirmed, it would represent the clearest evidence yet that supermassive black holes can be ejected from galaxies and enter intergalactic space. The mechanism that could produce such an ejection involves gravitational wave recoil. When two supermassive black holes spiral together during a galaxy merger and eventually collide, they emit a burst of gravitational waves. If those waves are emitted asymmetrically stronger in one direction than another, the merged black hole receives a kick in the opposite direction. Depending on the geometry of the merger, the kick can reach thousands of miles per second, potentially exceeding the escape velocity of the host galaxy. Simulations of galaxy mergers predict that gravitational wave recoil events occur, but producing kicks large enough to launch a supermassive black hole out of a massive galaxy requires a specific and somewhat rare configuration of black hole spins and mass ratios during the merger. Recoil is considered theoretically robust, but the rate of high kick events that could produce intergalactic black holes is uncertain. A second mechanism does not require extreme kicks. In a galaxy cluster environment where multiple galaxies merge over time, a three-body gravitational interaction between three supermassive black holes, one from each of three merging galaxies, can result in one black hole being ejected at high speed while the other two remain bound together. This process, sometimes called the black hole slingshot, may be more common in dense cluster environments. The candidate object announced in 2023 remains a candidate. Follow-up observations are needed to rule out alternative explanations, including the possibility that the streak is a jet from an active galaxy. The Hubble data is suggestive, but a single detection is not confirmation in this field. What the evidence does confirm is the plausibility. Black holes can receive gravitational kicks. Kicks can in principle exceed galactic escape velocities. Galaxy clusters produce the conditions for three-body interactions. The physics permits rogue black holes. The question is how often they are produced, and what they do as they drift through intergalactic space for billions of years, undetectable except by their gravitational effects on passing matter, an invisible object of immense mass, moving silently through the void. The difficulty is not imagining it. The difficulty is finding it, and the same difficulty applies to the dominant form of matter in the intergalactic environment, which we have never directly detected at all. Every filament in the cosmic web, every galaxy cluster, every large-scale structure in the observable universe sits inside something larger and invisible. Dark matter makes up roughly 85% of all matter in the universe. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. And the entire architecture of the cosmic web, the reason galaxies exist where they do and filaments connect, what they connect, is built on a framework of dark matter that formed before visible structures did. The evidence for dark matter is strong and comes from multiple independent directions. Galaxy rotation curves were among the earliest signals. Stars in the outer regions of galaxies orbit faster than the visible mass alone can explain, requiring additional unseen mass in extended halos around galaxies. Gravitational lensing, the bending of light from background objects by foreground mass, routinely detects mass in locations that contain little or no visible matter. The cosmic microwave background encodes the ratio of dark matter to ordinary matter in the early universe, and the measured ratio matches what modern, large-scale structure observations require. In the intergalactic medium, dark matter's presence is most clearly revealed at the scale of the cosmic web itself. The filaments that connect galaxy clusters are not made primarily of hot gas. The gas traces the filaments, but the gravitational spine of each filament is dark matter. Simulations show that dark matter filaments formed first, following slight density differences in the early universe, and ordinary matter fell in along those pre-existing dark matter structures. The gas and galaxies are passengers on a skeleton they did not build. Gravitational lensing surveys have mapped dark matter in the cosmic web directly, without relying on the ordinary matter that traces it. The Kilo-degree survey and the dark energy survey have used weak lensing as statistical measurement of how galaxy shapes are distorted by the mass between us and them to reconstruct the dark matter distribution across billions of light years. The maps produced by these surveys reveal a structure that matches what simulations predict. Massive dark matter concentrations at cluster positions, filamentary dark matter bridges between them, and large regions of dark matter deficit corresponding to the voids. At galaxy cluster scales, the most dramatic demonstration of dark matter's physical reality came from the Bullet cluster, a pair of galaxy clusters that collided roughly 150 million light-years away. During the collision, the ordinary hot gas in each cluster slowed because gas is affected by pressure and electromagnetic forces during collisions. The dark matter, which only responds to gravity, passed through the collision without slowing. X-ray observations showed the gas lagged behind the cluster cores. Gravitational lensing maps showed the mass concentration had moved ahead of the gas. The separation was direct evidence that dark matter behaves differently from ordinary matter in collisions, and that it is real, physically distinct, and capable of drift. What remains entirely unknown is what dark matter actually is at the particle level. Dozens of proposed particle candidates exist in theoretical physics, some within the framework of supersymmetry, some outside it. Decades of dedicated laboratory experiments designed to detect dark matter particles directly have, so far, produced no confirmed signal. The searches continue. The dark matter filaments carry the imprint of conditions in the very early universe. The pattern of their distribution across the cosmic web is so precise that it tests our fundamental model of cosmology at every scale. And some features of that pattern have started to show cracks. One collision reshaped the dark matter debate more than any other single observation. It happened between two galaxy clusters that plowed through each other at roughly 8 million miles per hour, and the aftermath gave astronomers something they had never had before: a picture of dark matter and ordinary matter physically separated from each other in space. The collision is called the bullet cluster because one of the two clusters passed through the other and emerged on the far side, leaving a characteristic bullet-shaped shockwave in the hot gas. The event happened in the past. The cluster pair sits roughly 3.8 billion light-years away, and we are observing the aftermath of the crossing. The hot gas in galaxy clusters is the dominant component of ordinary matter in those systems. There is far more hot gas in a cluster than there is mass in the stars of its galaxies. When the two clusters collided, this gas interacted. Pressure built up at the collision interface. The gas slowed and compressed, forming a bright shockwave in X-ray emission that NASA's Chandra X-ray Observatory mapped in detail. The X-ray observations clearly showed the gas concentrated near the center of the collision zone, lagging behind the cluster cores. The cluster cores themselves and the mass distribution in and around them were mapped using gravitational lensing. Light from background galaxies was bent by the foreground mass in the cluster pair, and the pattern of distortion revealed where the mass was concentrated. The result was striking. The mass peaks were located far from the X-ray gas. They sat on either side of the collision center, roughly coinciding with where the two cluster cores had ended up after passing through each other. This separation is exactly what happens if most of the cluster mass is dark matter. Dark matter does not interact electromagnetically. It has no pressure, no friction in the conventional sense. When two dark matter halos collide, they pass through each other, barely deflected, while the ordinary gas they previously contained gets left behind, compressed at the collision interface. The bullet cluster observation was published in 2006, and it remains one of the most widely cited pieces of evidence for dark matter in the scientific literature. The reason is straightforward. It is a direct, spatial demonstration of a difference in behavior between ordinary matter and the unseen mass component. The two kinds of matter went to different places after the collision. That separation is visible in the data. Some alternative theories of gravity, which attempt to explain galaxy rotation curves and large-scale structure without invoking dark matter, struggle with the bullet cluster. These theories typically modify how gravity behaves at low accelerations. In such frameworks, the gravity should still track the visible matter, including the gas. But in the bullet cluster, the gravitational lensing signal tracks something that is separated from the gas. For most alternative gravity theories, explaining this separation requires adding mass back, in which returns to the dark matter problem. Later observations of other colliding cluster systems have produced similar but less extreme results, some consistent with the bullet cluster picture, and some showing slightly different separations that have prompted ongoing debate about the exact nature of dark matter interactions. Whether dark matter is completely collisionless or has a small self-interaction cross-section is still being investigated. What we know from the bullet cluster is that the universe contains a dominant mass component that slips through ordinary matter collisions like a ghost. That component builds the cosmic web, holds galaxies in clusters, and shapes the environment that the hot, intergalactic gas fills. And that environment contains structures whose size stretches beyond what most people realize is possible. Remove the filaments, remove the clusters, remove the galaxies. What is left is the majority of the universe's volume, and it is almost completely empty. These regions are called cosmic voids, and the largest of them extend across distances that challenge intuition. A void is not simply a region with fewer galaxies. It is a coherent, expanding structure. In the early universe, matter was nearly uniform, but gravitational attraction gradually pulled matter away from slightly underdense regions toward denser ones. The denser regions grew into filaments and clusters. The underdense regions became emptier as matter left them, and they expanded as the surrounding structure pulled their borders outward. Voids are the negative space of the cosmic web, shaped by the same gravitational processes that built everything else, but defined by absence. The size of confirmed voids ranges from tens of millions to several hundreds of millions of light-years across. At those scales, the geometry of the void has direct cosmological implications. The rate at which voids expand encodes information about dark energy, the force driving the universe's accelerating expansion. A universe with more dark energy expands faster, and voids in such a universe grow larger and emptier more quickly. Comparing the observed properties of voids to model predictions provides an independent test of the dark energy content of the cosmos. Inside a cosmic void, galaxies do exist, but they are rare and tend to have distinctive properties. Observations show that galaxies found in void interiors are often smaller, less massive, and bluer than average. Bluer because they contain more young, hot, recently formed stars. The leading explanation is that void galaxies have had quieter histories, with fewer mergers and less interaction, because the distances between them are so large. Freed from the gravitational drama of dense cluster environments, void galaxies evolve more slowly and independently. The cosmic web boundary around a void is not a hard edge. Matter piles up at the void walls in thin sheets before organizing into filaments. These void boundaries are physically real and detectable. Surveys like the Sloan Digital Sky Survey and the BOSS survey have mapped void catalogs containing thousands of individual voids, tracking their sizes, shapes, and positions across large fractions of the observable universe. Dark energy leaves a measurable imprint on how the microwave background looks in the direction of large voids. A photon traveling through a void gains a tiny amount of energy as the void's gravitational potential changes during the photon's crossing, a confirmed effect called the integrated Sachs-Wolf effect. Detecting this effect requires correlating void positions with temperature fluctuations in the microwave background. Multiple research teams have reported detections of this signal, providing yet another independent line of evidence connecting void structure to dark energy. Voids are not inert. They are dynamic regions where matter is actively being pulled toward their boundaries by the surrounding structure. Galaxy surveys that slice through voids show systematic patterns of galaxy velocity, galaxies near void centers, moving outward, galaxies near void edges, moving inward, a coherent flow pattern that reflects the void's expansion. Some voids border other voids across thin sheets, creating a connected network of emptiness that mirrors the filamentary network of matter. The universe is simultaneously a web of connected structures and a web of connected absences, interlocked like two complementary patterns traced from the same template. One specific void, discovered decades ago, became famous for its sheer size and the questions it provoked. In 1981, a team of astronomers surveying galaxies in a region of sky called Boötis found something that initially looked like a gap in their data. A region roughly 330 million light-years across contained almost no galaxies. They checked their instruments. They reviewed the observations. The result held. There was a real, enormous region of space that was nearly empty, where there should have been hundreds of galaxies based on the surrounding distribution. The Botez void, as it became known, remains one of the largest confirmed supervoids in the observable universe. At 330 million light-years in diameter, it sits comfortably within the range of the largest structures that standard cosmological models can produce through gravitational evolution. It is large, but it is not impossibly large, which is an important distinction, because early reactions to the void sometimes suggested it posed a fundamental problem for cosmology. Current understanding places it within the expected distribution of large-scale underdensities, though it remains one of the most striking examples. What makes the Botez void particularly useful scientifically is its relatively close distance of roughly 700 million light-years, which allows detailed surveys of its interior. Later galaxy surveys have found that it is not completely empty. A handful of galaxies exist inside it, but their number is dramatically below what the surrounding density would predict. The void interior appears to have actively expelled or simply never accumulated the matter needed for extensive galaxy formation. The few galaxies found inside the void are also interesting in themselves. Their properties are consistent with what has been found in other void environments. They tend to be less massive and show signs of quieter evolutionary histories than galaxies in denser regions. Inside the Botez void, galactic evolution proceeded differently, shaped by the extreme isolation of the environment. The void's shape is roughly spherical, which is typical for isolated voids that have been expanding for long periods. More elongated void structures tend to appear where multiple overlapping underdense regions merge, or where the surrounding filament structure influences the expansion geometry. The near-spherical shape of the Botez void suggests it developed in a relatively uniform gravitational environment. One recurring popular claim is that the Botez void is too large to have formed through normal gravitational processes in the age of the universe. This claim is disputed in the scientific literature. Simulations of the cosmic web under standard cosmological parameters do produce supervoids of comparable size, given sufficient survey volume to find rare events. The Botez void may be a statistical outlier, a large but naturally occurring fluctuation, rather than a violation of the standard model. What it does represent unambiguously is the scale at which the universe organizes itself into absence. A sphere more than 300 million light-years across, containing only a trickle of galaxies in a space that should, by average, host hundreds. The gravitational machinery that built the cosmic web pulled matter away from this region over billions of years, leaving behind something that feels, by almost any measure, profoundly empty. But the Botez void, for all its scale, is relatively nearby. Farther out, in the pattern of the ancient radiation left over from the Big Bang, there is an anomaly whose origin is genuinely unresolved and whose explanation, some researchers believe, may require something that does not fit the standard picture at all. The oldest light in the universe is the cosmic microwave background, a faint glow of radiation that fills the entire sky, the thermal afterglow of the hot early universe. From when it was roughly 380,000 years old, it is extraordinarily uniform. Temperature variations across the entire sky amount to differences of about 1 part in 100,000. But within that near-perfect uniformity, one region stands out. In the southern sky, in the direction of the constellation Eridanus, there is a patch of the cosmic microwave background that is colder than the surrounding average by a small but statistically significant amount. It is called the cold spot, and it was identified with confidence following data from NASA's Wilkinson Microwave Anisotropy Probe satellite in the early 2000s. Subsequent data from the European Space Agency's Planck satellite confirmed its existence with higher resolution. The cold spot spans roughly 5 degrees across the sky, 10 times the width of the full moon as seen from Earth, making it the largest individual anomaly identified in the microwave background. Its statistical significance is real. though there is active debate about exactly how unlikely it is, given the many ways one could define and look for anomalies in a complex dataset. Several explanations have been proposed. The most widely discussed involves a supervoid along the line of sight between us and that region of the microwave background. As explained earlier, a photon traveling through a large void can lose a tiny amount of energy through the integrated Sachs-Wolf effect as the void expands during the photon's crossing. A large enough supervoid along the line of sight to the cold spot could in principle produce a colder than average patch in the microwave background as observed today. In 2015, a research team using Galaxies survey data reported finding a supervoid in the direction of the cold spot at a distance of about 3 billion light-years. The void they identified is roughly 1.8 billion light-years across. If confirmed at that size, it would be among the largest voids ever detected. However, subsequent analyses have questioned whether this void is large enough and underdense enough to produce the full temperature difference seen in the cold spot. The supervoid explanation may account for part of the anomaly, but probably not all of it. Other proposals include a rare but statistically possible fluctuation in the early universe, a texture defect in the structure of space produced by physics in the very first moments after the Big Bang, or a signature of cosmic topology, the possibility that the universe wraps around on itself in a way that produces specific patterns on large scales. None of these explanations is confirmed. None can currently be ruled out. What is confirmed is that the cold spot exists, that it is unusual, and that its origin remains an open question in observational cosmology. The fact that multiple research groups using different instruments and analysis methods have reproduced the detection makes it credible. The fact that no single proposed explanation fully satisfies the data makes it genuinely unresolved. The standard cosmological model predicts no feature of this size and prominence at this location. That does not mean the model is wrong. Anomalies appear in any large dataset, and one anomaly in the full microwave sky is not enough to overturn a model supported by thousands of other observations. But it is a flag, a specific, measurable feature that demands an explanation the scientific community does not yet have. And if the cold spot is connected to the largest void structures in the universe, that connection points toward an even more extreme feature of the cosmic architecture, one whose sheer size is difficult to reconcile with the universe we thought we were living in. Every generation of astronomers has found that the universe is bigger and more structured than the previous generation believed. Structures once thought to be the largest known were eventually revealed to be parts of something larger. This pattern has repeated itself at every scale until the current theoretical limit, which is set by cosmology itself, above roughly 1.5 billion light-years in scale. The universe should begin to look uniform. Structures larger than that should not form through gravity alone in the time the universe has had to evolve. The Hercules Corona Borealis Great Wall exceeds that limit significantly. It is a concentration of gamma-ray burst sources, and by extension, the massive galaxies that produce them, spanning an estimated 10 billion light-years across. That is roughly 1/13 of the diameter of the entire observable universe, distributed in a region with a higher than average density of gamma-ray bursts compared to surrounding areas. Gamma-ray bursts are the most energetic explosions known in the universe, associated with the deaths of massive stars and the mergers of neutron stars. They are detectable from billions of light-years away and serve as markers of where massive star formation is occurring. A region with an unusually high concentration of gamma-ray bursts indicates a region with a higher than average concentration of the galaxies that produce them, which implies an overdensity of matter on a large scale. The Hercules Corona Borealis Great Wall was identified through statistical analysis of gamma-ray burst catalogs, published by a research team in 2014 and subsequently discussed and debated in the scientific literature. The reported extent of the structure significantly exceeds the theoretical upper limit of roughly 1.5 billion light-years that standard cosmology allows for coherent large-scale structures. The debate around this structure is serious and ongoing. Critics have raised questions about whether the apparent concentration of gamma-ray bursts reflects a true physical overdensity of matter, or could instead result from observational selection effects, the way the detectors that record gamma-ray bursts are not uniformly sensitive across the sky and across different distances. If detection probability varies with direction or redshift, a statistical artifact could mimic the appearance of a genuine large-scale structure. Proponents of the structure argue that the clustering signal is statistically robust even after accounting for known selection effects, and that the concentration is too extreme to be explained by observational bias alone. The debate has not been resolved. Follow-up work using other traces of large-scale structure galaxy surveys, for example, has not yet fully mapped the region to the depth and coverage needed for a definitive test. If the Hercules Corona Borealis Great Wall is a real physical structure, it poses a genuine challenge to standard cosmology. A structure 10 billion light-years across requires either far more time to form than the universe has had, or some mechanism beyond standard gravitational collapse to explain its existence. That would be significant. The honest position is uncertainty. The structure may be real and anomalous. It may be a statistical artifact. The evidence available today is suggestive but inconclusive. That uncertainty is scientifically meaningful. It identifies a region of the observational universe that demands better data, and the tools being built right now to gather that data may also resolve a deeper tension in the cosmic architecture, one that sits at the boundary between the web of filaments and the voids between them. The cosmic web organizes everything up to a certain scale. Below that scale, matter clusters into galaxies, clusters, and filaments in ways that simulations reproduce with remarkable accuracy. Above that scale, the universe should become featureless, statistically uniform, a smooth sea of evenly distributed matter and radiation. Cosmologists call this the homogeneity scale, and standard theory places it at roughly 300 million light-years. At scales larger than that, no structure should dominate. The cosmic web becomes statistical background. Any apparent pattern becomes indistinguishable from random noise. Several observations have tested this boundary, and the results have introduced a tension that is now an active focus of cosmological research. The issue is not that individual anomalies have been found. Any survey will produce outliers. The issue is that the distribution of large-scale structures, when measured precisely and across large enough volumes, shows subtle but consistent deviations from what the standard model predicts. One of the clearest signals involves the way galaxies cluster on different scales. Surveys covering hundreds of millions of light-years find galaxy clustering that matches predictions well. At larger scales, some analyses have found slightly more clustering than expected, or structures slightly more prominent than the smooth transition the model requires. These deviations are not dramatic on their own, but they appear in multiple independent datasets. The baryon acoustic oscillation signal is one of the most reliable rulers in cosmology. Sound waves in the early universe traveled through the hot plasma until the universe cooled enough for atoms to form, roughly 380,000 years after the Big Bang. At that moment, the sound waves froze, leaving a preferred scale imprinted in the distribution of matter, a ring of slightly higher galaxy density at a scale of roughly 500 million light-years. This ring appears in galaxy surveys as a statistical bump, and its scale provides a standard reference for measuring distances across the cosmos. When the baryon acoustic oscillation scale is measured using different galaxy surveys and compared, the results are consistent with standard cosmology at high precision, one of the model's major successes. But some analyses of the full shape of the matter-power spectrum, which describes how strongly matter clusters at every scale simultaneously, have found mild discrepancies with predictions at large scales that remain under active investigation. There is also the sigma-8 tension, a disagreement between the strength of matter clustering predicted from the early universe, microwave background measurements, and what direct measurements of large-scale structure find today. Multiple independent measurements using gravitational lensing surveys have found that matter in the late universe appears to cluster slightly less tightly than the microwave background data predicts. The discrepancy is not large enough to overturn the model, but it is persistent across different methods and datasets. Whether these tensions point to unknown physics, a modification of the standard cosmological model, or result from subtle systematic errors in measurements, is the central question. Upcoming surveys, including the Euclid Space Telescope launched by the European Space Agency in 2023, the Vera Rubin Observatory in Chile, and the Dark Energy Spectroscopic Instrument, are designed to map large-scale structure at unprecedented precision across enormous volumes. If the tensions persist at higher statistical significance, the pressure on the standard model will grow. The cosmic web is real. Its broad features are confirmed, but at the edges of its scale, where it fades into the homogeneous background of the universe, the data is telling us something that the model does not fully account for. And that is where the story is still being written. Before any galaxy existed, the universe was a hot, dense plasma, a soup of particles and radiation so tightly coupled that sound waves moved through it. Real acoustic waves. Pressure ripples traveling outward from every slight density variation in the early cosmos. For roughly 380,000 years, those waves propagated through the plasma at more than half the speed of light. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. That transition happened fast, in cosmic terms. When it did, the plasma that had been carrying the sound waves simply stopped being a plasma. The waves froze. The ripple pattern locked into the distribution of matter at that exact moment, imprinted across the universe like a ring stamped into wet concrete. That frozen pattern is called the baryon acoustic oscillation signal, and it survives to this day. It shows up as a statistical preference. Galaxies are slightly more likely to be separated by a specific distance, roughly 500 million light-years, than by distances just above or below that value. The preference is faint a few percent above the baseline clustering rate, but it appears consistently in every large galaxy survey conducted over the past 2 decades. The reason it matters is precision, because the physical scale of those early sound waves can be calculated from first principles, from the temperature and composition of the early universe, as measured through the cosmic microwave background astronomers know exactly how large that preferred separation should be. Measuring how large it appears in galaxy surveys at different distances tells them how much the universe has expanded between then and now. The baryon acoustic oscillation scale functions as a cosmic ruler, calibrated by the physics of the early universe, and readable in the positions of galaxies billions of light-years away. The Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey program, measured this signal across a volume containing more than 1 million galaxies and produced some of the most precise distance measurements in the history of observational cosmology. The results matched the standard model's predictions at high precision and provided independent confirmation of the universe's expansion history. What gives the signal its power as a tool is its independence from other measurement methods. Measurements using Type Ia supernovae as standard candles and measurements using the cosmic microwave background both independently point to the same cosmological parameters. Baryon acoustic oscillations provide a third, geometrically distinct method. When all three agree, confidence in the standard model strengthens. When they diverge, it signals something worth investigating. That divergence exists right now in the form of the Hubble tension, a persistent disagreement between the expansion rate of the universe, measured using early universe data, including baryon acoustic oscillation measurements, and the rate measured using late universe methods like supernovae and certain lensing techniques. The gap is small in absolute terms but statistically significant, and it has resisted resolution through better data or error correction for over a decade. Whether the Hubble tension reveals new physics, a modification to dark energy, an additional particle species in the early universe, something else, or reflects an unidentified systematic error in one or more measurement chains remains the most actively contested question in modern cosmology. The frozen sound waves from the early universe contain the answer to that question, buried in the statistical pattern of galaxy positions across hundreds of millions of light years. Every new survey that maps more galaxies at greater depths is listening more carefully to those ancient vibrations. The signal is there. The full meaning is still arriving. And the medium through which all of this ancient light and these ancient signals must travel, the intergalactic medium in the modern universe, has its own filtering effect on what we can and cannot read. Everything we know about the distant universe arrived as light, radio waves, X-rays, infrared, visible, all forms of electromagnetic radiation, all traveling through the intergalactic medium before reaching our telescopes. That medium is not neutral. It absorbs, it scatters, it alters wavelengths depending on its temperature, density, and chemical composition. The farther we look, the more it filters what we see. The most dramatic filtering effect happens at the greatest distances. When astronomers look back toward the first billion years of cosmic history, the light from early galaxies and quasars must pass through the neutral hydrogen gas that dominated the intergalactic medium before reionization. The process by which energetic radiation from early sources burned away that neutral gas and made the universe transparent. Before reionization was complete, the intergalactic medium was essentially opaque to certain wavelengths of ultraviolet light. This opacity appears in quasar spectra as the Gunn-Peterson trough, a near-total absorption feature that marks the transition between the transparent, modern universe and the neutral, foggy, young universe. The Gunn-Peterson trough was first predicted in 1965 and definitively detected in 2001 by a team studying distant quasars with the Keck Observatory. Finding this absorption feature in the spectra of quasars at high redshift confirmed that the intergalactic medium was still substantially neutral at roughly 1 billion years after the Big Bang, providing direct evidence that reionization was still underway at that epoch. Closer to our own time, the intergalactic medium is mostly ionized and largely transparent to most wavelengths, but it still leaves detectable traces on what passes through it. The Lyman alpha forest, those hundreds of absorption lines in quasar spectra, corresponding to intervening clouds of hydrogen, reflects the clumped filamentary structure of the modern intergalactic medium. Each line is a real cloud. The pattern of lines encodes the thermal state of the gas, the intensity of background radiation, heating it, and the large-scale structure it traces. At high energies, the intergalactic medium absorbs gamma rays through a different process. When a high-energy gamma-ray photon collides with a lower-energy photon from the extragalactic background light, the cumulative infrared and optical radiation from all the stars and galaxies that have ever existed, the two photons can annihilate and produce a pair of particles. This process, called pair production, removes high-energy gamma rays from our view at distances that depend on the photon energy. It creates an effective horizon for gamma-ray astronomy, beyond which very high-energy gamma rays cannot reach us. By measuring how many high-energy gamma rays are absorbed at different energies and distances, astronomers can reconstruct the density of the extragalactic background light, which in turn tells them how many stars the universe has produced over its history. The intergalactic medium here functions as a measuring instrument embedded in the universe itself. Fast radio bursts have added another tool. These millisecond pulses of radio energy, detected from billions of light years away, are dispersed by the electrons in the intergalactic medium. Different radio frequencies arrive at slightly different times, with the delay proportional to the number of electrons along the line of sight. By measuring that dispersion, astronomers can directly estimate the total column of ionized gas between us and the source. Multiple fast radio bursts detected at known distances have been used to weigh the intergalactic medium, and the results are consistent with the missing baryon detections, independently confirming that the warm-hot intergalactic filaments contain roughly as much ordinary matter as the galaxies. The universe communicates through the medium it made. Every signal arriving at our telescopes has been shaped by that medium. Learning to subtract the filter reveals what the filter contains. And what it contained in the past, before it cleared, is one of the most dramatic phase transitions in cosmic history. For roughly 400 million years after the Big Bang, the universe was dark. Stars and galaxies had not yet formed in significant numbers. The intergalactic medium was filled with neutral hydrogen gas that blocked ultraviolet light. The cosmos existed in a state that astronomers call the cosmic dark ages, a period that left no visible light, only the faint radio glow of hydrogen. Then the first sources of intense radiation switched on. The first massive stars formed inside the earliest galaxy-scale structures, burning hot and bright for only a few million years before exploding. Quasars, powered by young supermassive black holes, began to radiate with extraordinary luminosity. Both kinds of source pumped out large quantities of ultraviolet photons, and those photons had enough energy to strip electrons away from neutral hydrogen atoms to ionize them. The process called reionization began locally. Each new source of radiation carved out a bubble of ionized gas around itself. The bubble expanded as more photons were produced. Over time, neighboring bubbles grew large enough to merge. As more and more sources formed across the universe, their ionization bubbles overlapped and connected, and the neutral fog of the intergalactic medium was burned away from the inside out. Reionization was not instantaneous. The process appears to have begun around 150 to 250 million years after the Big Bang, and was largely complete by roughly 1 billion years after. The evidence for this timeline comes from multiple directions. Quasar spectra at different distances show the transition from the opaque Gunn-Peterson absorption at high redshift to the partial absorption of the Lyman alpha forest at intermediate distances to the largely transparent intergalactic medium we observe today. The James Webb Space Telescope has pushed observations of this transition era to previously inaccessible distances. Webb has detected galaxies within the first few 100 million years of cosmic history, with ultraviolet luminosities sufficient to contribute meaningfully to reionization. A key question for the field is whether star-forming galaxies, rather than quasars, were the dominant reionization source, and Webb's data increasingly supports a significant galactic contribution, particularly from numerous small, faint galaxies whose light was previously too dim to detect. Mapping exactly how and when reionization proceeded across different regions of the universe requires observations of the 21-centimeter hydrogen emission line from the neutral intergalactic medium before and during reionization. Radio telescopes are attempting this measurement, but it is technically extremely challenging. The signal is buried under interference from radio sources both on Earth and in our own galaxy. Early results from arrays like the Hydrogen Epoch of Reionization Array are beginning to place constraints on the timing and extent of reionization, and the Square Kilometer Array is expected to map the process in detail when it reaches full operation. Reionization matters beyond its role as a historical transition. The photons that reionized the intergalactic medium came from stars and black holes forming inside the first galaxies. Those same photons, heated surrounding gas, influenced which halos could form galaxies and set the thermal state of the intergalactic medium that we measure today. The temperature of intergalactic gas seen in the Lyman alpha forest retains a memory of when it was reionized. The universe remade the medium it expanded through, and having remade it, continued to fill it with travelers that have no home galaxy and are still in motion right now. The intergalactic medium is not just filled with gas, magnetic fields, and radiation. It contains solid objects, bodies with mass and gravity, small enough to be invisible to most telescopes, and numerous enough that their total population across the universe may be staggering. These are rogue planets, worlds without stars, and their confirmed existence in interstellar space raises real questions about how many of them drift through the even larger voids between galaxies. Rogue planets are a confirmed phenomenon. They form in two ways. Some are ejected from forming planetary systems when gravitational interactions between young planets in a disk around a star kick one member out of the system entirely. Others may form directly from collapsing gas clouds too small to ignite as stars. Both mechanisms are predicted by planetary formation theory and are supported by observations. Direct detection of rogue planets is difficult because they emit no light of their own. The method that has produced the strongest evidence is gravitational microlensing. When a rogue planet passes in front of a more distant star, its gravity bends and magnifies the star's light in a characteristic way. The event is brief hours to days, and the shape of the brightening curve reveals the mass of the lensing object. Masses in the planetary range, without any associated host star signal, indicate a free-floating planet. The optical gravitational lensing experiment survey and observations by the microlensing observations in astrophysics collaboration have detected multiple rogue planet candidates in this way over the past 2 decades. A study published in 2021 reported detections of events consistent with Earth mass rogue planets, suggesting they may be extraordinarily common, potentially more common than stars. Some estimates place the number of free-floating planets in our galaxy at several times the number of stars. The uncertainties are large, but the lower end of the estimates is still a very large number. Within our own galaxy, rogue planets drift through interstellar space, the void between stars rather than the vast intergalactic void. But the processes that eject planets from forming systems operate in galaxies throughout the universe, and the same gravitational dynamics that eject stars from galaxies during mergers, the tidal stripping and slingshot mechanisms discussed earlier, could in principle carry planetary mass objects outward into true intergalactic space, though direct evidence for intergalactic rogue planets specifically remains out of reach of current instruments. The detection of the interstellar object called Oumuamua in 2017, and subsequently the confirmed interstellar comet Borisov in 2019, demonstrated directly that small, solid objects can travel between stellar systems. Neither was a planet mass object, but both confirmed that the interstellar medium is not as sterile as it might appear. Objects originating around other stars pass through our solar system. The interstellar medium is trafficked by debris from countless planetary systems. The Nancy Grace Roman Space Telescope, expected to conduct a large microlensing survey of the galactic bulge, will detect potentially thousands of rogue planet candidates. Its data will dramatically improve estimates of the rogue planet population and constrain the mass distribution of these objects. What emerges from this is a universe whose between-galaxy spaces are populated not just with diffuse gas and dark matter, but with solid objects from broken planetary systems, hypervelocity stars from galactic centers, and possibly ejected black holes from merger events. The void is occupied. It is not quiet. And moving through that occupied void are flashes of energy so brief and so powerful that for years, no one was sure they were real. A radio telescope records silence for hours, then, in the space of a millisecond, receives a burst of radio energy equivalent to the power of hundreds of millions of stars, then silence again. The burst lasts less time than the blink of an eye. It comes from billions of light years away, and it carries, encoded in the delay between its different radio frequencies, a precise measurement of all the matter it passed through on its journey across the intergalactic medium. Fast radio bursts are real. The first was discovered in archival data from the Parkes Observatory in Australia in 2007, and initially met with skepticism. The signal's properties, its brightness, its duration, its dispersion, matched a source at cosmological distances, but the energy implied was extraordinary. It took years of follow-up detections, including bursts caught in real time, to confirm that fast radio bursts are genuine astrophysical phenomena, originating billions of light years from Earth. The dispersion measure is the key piece of physics that makes fast radio bursts cosmologically useful. Radio waves traveling through a plasma-ionized gas are slowed in a frequency-dependent way. Lower frequency radio waves are slowed more than higher frequency ones. When a fast radio burst travels across billions of light-years of intergalactic medium, this effect spreads the burst in time. The high-frequency components arrive first. The low-frequency components arrive slightly later. By measuring this spread, astronomers can calculate the total number of free electrons along the line of sight from source to Earth. Because the intergalactic medium contributes the dominant portion of that electron column for distant fast radio bursts, measuring the dispersion gives a direct probe of the ionized gas in intergalactic space between us and the source. Comparing dispersion measures from fast radio bursts at known distances has allowed astronomers to independently measure the density of the intergalactic medium and confirm that its baryon content is consistent with the values derived from other methods. Fast radio bursts became a practical weighing scale for the universe's missing matter. The source of fast radio bursts is now at least partially identified. In 2020, a magnetar in our own galaxy, a neutron star with an extraordinarily powerful magnetic field, produced a fast radio burst detectable from within the Milky Way. This confirmed that at least some fast radio bursts originate from magnetars. The mechanism involves the violent release of magnetic energy stored in the star's crust, producing a burst of radio emission in milliseconds. Whether all fast radio bursts come from magnetars, or whether multiple source classes exist, remains an open question. Repeating fast radio bursts, sources that produce multiple bursts over time, allow detailed localization and host galaxy identification. The Australian Square Kilometre Array Pathfinder and the Canadian Hydrogen Intensity Mapping Experiment have detected thousands of fast radio bursts, dramatically expanding the known population. Each detected burst is a data point in a map of the intergalactic medium. The distribution of dispersion measures across many bursts encodes the statistical properties of intergalactic gas along different lines of sight. Variations in dispersion measure beyond what the average intergalactic density predicts could reveal the presence of dense filaments or voids, specifically along individual lines of sight, allowing fast radio bursts to trace the cosmic web structure directly. A millisecond event becomes a decade of cosmological information. The void between galaxies, traversed in an eye blink of signal, has been quietly recording everything it contains. And what it contains, at the largest scales, presses against the boundary of what the universe's age and physics should allow. The most energetic events in the universe since the Big Bang are not supernovae. They are not gamma-ray bursts. They are the collisions of galaxy clusters, systems containing hundreds or thousands of galaxies, vast reservoirs of hot gas, and enormous dark matter halos, slamming into each other at speeds of millions of miles per hour. The energy released in such collisions exceeds the combined output of all the stars in both clusters over their entire lifetimes. Galaxy clusters collide because the cosmic web drives them together. Filaments channel matter toward nodes, and the clusters sitting at those nodes grow by accreting smaller systems and occasionally merging with other large clusters. The rate of cluster mergers was higher in the past when the universe was denser, but it continues today across the observable universe. The collision is not primarily between the galaxies themselves. The galaxies are relatively small and widely separated. During most cluster mergers, the galaxies pass through each other's space without direct contact. The distances between individual galaxies are large enough that collisions between them are rare, even when their parent clusters merge. What collides violently is the hot gas that fills the space between galaxies within each cluster. That intracluster gas, which contains more mass than all the stars in the cluster combined, experiences the collision in full. Pressure builds at the interface between the two onrushing gas reservoirs. A shock wave develops, moving outward through the gas and heating it. The shocked gas emits X-rays that can be detected across billions of light-years. The temperature jump at the shock front, measured by X-ray satellites, reveals how fast the collision is proceeding. In the bullet cluster, the The shock velocity inferred from the gas temperature jump is roughly 8 million miles per hour, one of the highest confirmed velocities for a large astrophysical structure. Cluster mergers also accelerate particles to high energies. Electrons spiraling through the magnetic field of the intracluster medium, boosted by the shock wave, emit radio waves. These radio relics arc-shaped structures of diffuse radio emission tracing the shock waves of merging clusters have been detected in dozens of cluster systems. Their properties map the geometry of the merger and the strength of the cluster magnetic field. One implication of cluster mergers for intergalactic science involves the gas that gets displaced into the surrounding environment. Mergers are turbulent. Gas that belonged to the intracluster medium before the collision can be displaced outward into what was previously empty intergalactic space. This expelled gas adds to the population of warm material in the broader filamentary environment and blurs the boundary between the intracluster medium and the intergalactic medium surrounding it. The largest cluster mergers observed are called superclusters in formation, not yet collapsed into a single bound object, but in the process of falling together under gravity. The Shapley supercluster, the largest concentration of galaxies in the nearby universe, is an example of a region where multiple massive clusters are gravitationally bound but still separated. Future mergers there will produce collisions at even larger scales than any currently observed. Mapping cluster collisions across cosmic time has also revealed something about dark energy. The rate at which clusters collide depends on how fast the universe is expanding. A universe dominated by dark energy expands faster, which means clusters drift apart more rapidly at late times, reducing the merger rate in the recent epoch. Comparing the observed cluster merger rate at different distances provides a history of how dark energy's influence has evolved, a test that complements baryon acoustic oscillation and supernova measurements. The aftermath of every cluster collision sends shockwaves into intergalactic space and ejects material from the densest environments into the broader cosmic web. The boundary between cluster and void is alive with the record of those events. The cosmic web does not just organize matter, it delivers it. The filaments connecting galaxy clusters are not static bridges. They are active channels through which gas flows toward denser regions, and that flowing gas is the primary mechanism by which many galaxies acquire the material they need to form stars. The relationship between intergalactic filaments and galaxy growth is direct, confirmed by both observation and simulation. In the early universe, galaxies grew rapidly. Star formation rates, in the first few billion years of cosmic history, were dramatically higher than today some galaxies. Formed stars at rates hundreds of times greater than our own Milky Way manages now. Sustaining those rates required a continuous supply of cold gas, cold enough to collapse and form stars. The question was where that gas came from. Two modes of gas delivery were predicted by simulations. Hot accretion involves gas that falls into a galaxy's gravitational halo. Shock heats to the halo temperature and then slowly cools and settles into the galaxy over a long time. Cold accretion involves gas that flows along dense filaments directly into the galaxy without heating significantly, arriving cold enough to feed star formation immediately. In massive halos at high redshift, cold streams, thin threads of cool gas threading down through the hot halo atmosphere along the filament directions were predicted to be the dominant supply channel. Observational evidence for cold streams is accumulating. The dense hydrogen clouds associated with some distant galaxy systems show kinematic signatures, velocity patterns consistent with gas flowing inward along specific directions rather than settling uniformly. Some of the most intensely star-forming galaxies at early cosmic epochs show gas geometries consistent with cold stream feeding. The James Webb Space Telescope has begun probing the gas environments around high redshift galaxies with sufficient sensitivity to test these predictions more directly than was previously possible. At lower redshifts, closer to the present filament, feeding still operates but at reduced rates. As the universe expanded, the density of intergalactic filaments decreased. As massive halos grew, the shock-heated halo gas became a more significant barrier to cold streams. Star formation rates declined across the universe in parallel with the reduced supply of cold gas, a connection that simulations naturally reproduce. Observations using the Hubble Space Telescope and subsequent surveys have detected hydrogen gas bridges between galaxies in group and cluster environments, material strung between galaxies by gravitational interaction and bridges, representing the residue of filamentary gas that once connected them to the broader web. Some of these bridges span millions of light years and contain enough mass to fuel significant star formation if it could cool and collapse. The filaments also carry metals elements heavier than hydrogen and helium, produced by stars and expelled from galaxies in supernova-driven winds. These metal-enriched outflows travel into the intergalactic medium and are transported along filaments. Detecting the metal content of intergalactic gas along filaments allows astronomers to trace the history of galactic outflows and constrain how much material galaxies have expelled compared to how much they retained. Every galaxy we observe is downstream of a filament. Its size, its star formation rate, its chemical composition all carry a record of how its filament delivered gas, and for how long. The intergalactic medium is not a passive backdrop to galaxy evolution. It is the active supply chain, and that supply chain operates within a large-scale framework whose geometry encodes information about the universe's most mysterious component. Dark energy is the name given to whatever is driving the universe's expansion to accelerate. It was confirmed in 1998 through observations of distant supernovae, which showed that the universe is not just expanding, it is expanding faster and faster over time. Dark energy currently makes up roughly 68% of the total energy content of the universe, and its effects are written into the large-scale structure of the cosmic web in ways that future surveys are designed to read. The mechanism is straightforward at a broad level. Dark energy opposes the gravitational tendency of matter to clump. In the early universe, when matter density was high, gravity dominated and structure grew rapidly. Filaments thickened, clusters formed, voids emptied. As the universe expanded and matter density dropped, dark energy's influence became more significant. Structure growth slowed. The rate at which clusters accumulate new mass, the rate at which filaments thicken, the rate at which voids expand, all of these changed as dark energy came to dominate the energy budget. The result is that the pattern of the cosmic web encodes a history of the competition between gravity and dark energy. The amplitude of galaxy clustering at different scales, how strongly galaxies avoid or follow each other encodes the growth rate of structure over time. Measuring this growth rate at multiple cosmic epochs provides a direct test of how dark energy has behaved through history. The simplest version of dark energy is the cosmological constant, a fixed energy density associated with empty space itself, uniform everywhere and constant over time. In this model, dark energy does not evolve. Its strength today is the same as it was billions of years ago. The standard cosmological model assumes this form of dark energy, and for decades it fit the available data adequately. Recent data from the Dark Energy Spectroscopic Instrument, operating at the Kitt Peak National Observatory in Arizona, has mapped the positions of tens of millions of galaxies and quasars across a large fraction of cosmic history. Its first major results, released in 2024, showed hints that dark energy may have been slightly different in the past than it is today, a possible evolution in its strength over time. If confirmed at higher statistical significance, this would challenge the cosmological constant model and point toward a dynamic form of dark energy. The cosmic web structure is one of the most sensitive tests of dark energy because it reflects the integrated history of structure growth rather than a single snapshot. Baryon acoustic oscillations, galaxy clustering statistics, void abundances, and cluster counts all probe different aspects of the same underlying competition between gravity and dark energy. Using all of these probes together reduces the chance that any single systematic error drives the result. The Euclid satellite, launched in 2023 by the European Space Agency, will map the cosmic web across 10 billion years of cosmic history using both galaxy clustering and weak gravitational lensing. Its data, combined with results from the Vera Rubin Observatory's legacy survey of space and time beginning operations in the mid-2020s, will provide the most precise characterization of dark energy yet attempted. The cosmic web is a thermometer for dark energy. Its filaments grow or thin depending on how strong dark energy is. Its voids expand or stagnate depending on how the competition between repulsion and attraction has played out over billions of years. Every map of large-scale structure is a chapter in the history of whatever is driving the universe apart. And understanding what drives the universe apart may also help explain the deepest tension in modern cosmology, one that no current model has resolved. Two completely independent methods for measuring how fast the universe is expanding consistently give different answers, and the gap between them has grown more significant with every new dataset. This disagreement is called the Hubble tension, and it is currently the sharpest unresolved problem in observational cosmology. The Hubble constant measures how fast the universe expands, specifically, how quickly galaxies are moving apart relative to their distance from each other. The two methods that disagree measure it at different points in cosmic history. The first method uses the cosmic microwave background. By analyzing the detailed pattern of temperature fluctuations in this ancient radiation and combining that pattern with the standard cosmological model, astronomers predict what the expansion rate should be today. The Planck satellite, which produced the most precise microwave background measurements ever made, gives a Hubble constant of roughly 67 kilometers per second per megaparsec. The second method uses a distance ladder built from nearby objects, type Ia supernovae, which have a known intrinsic brightness and can be seen across billions of light years, serve as the outermost rung. Their brightness is calibrated against Cepheid variable stars, pulsating stars, with a known relationship between pulsation period and intrinsic brightness, which are in turn calibrated against geometric parallax measurements in our own galaxy. This distance ladder approach consistently gives a Hubble constant of roughly 73 kilometers per second per megaparsec. The two values differ by roughly 8 to 9%, with a statistical significance that has grown to around 5 standard deviations. In some analyses, well above the threshold normally required to claim a genuine discrepancy. Both measurements have been cross-checked extensively. The Planck results have been reproduced by independent analyses and are internally consistent. The supernovae-based measurements have been reproduced using the James Webb Space Telescope, which has sharper resolution than Hubble and can independently check the Cepheid calibrations. Webb's results agreed with the existing distance ladder results, making it less likely that the discrepancy is a simple calibration error. Several proposed explanations for the tension involve modifying the standard cosmological model. Early dark energy, a form of dark energy that existed briefly in the early universe before fading, could in principle reduce the sound horizon scale at the time of reionization, shifting the microwave background prediction for the Hubble constant upward. Additional neutrino species in the early universe could achieve a similar effect. Various other modifications have been proposed and tested against the data. None of the proposed solutions fully resolves the tension without creating new disagreements with other observations. The tension may require a modification that has not yet been conceived. It may also have a more mundane explanation that emerges from improved understanding of astrophysical systematics in the distance ladder. The current state of the field is genuine uncertainty about which of these possibilities is correct. What makes the Hubble tension significant beyond its technical details is its position as the clearest indication that something in the standard cosmological model may be incomplete. The model succeeded in predicting the cosmic microwave background, the abundances of light elements, the large-scale structure of the universe, and dozens of other observables. A persistent, significant tension in its most fundamental parameter, the expansion rate of the universe, is a signal worth taking seriously. The intergalactic medium carries the Hubble tension in the data encoded in fast radio bursts, in baryon acoustic oscillations, in cluster counts. Every new measurement of the cosmic web tightens the constraint on which explanation is correct. A cosmic void is the closest thing the universe produces to a controlled laboratory for gravity at the largest scales. Inside a void, matter density is extremely low. Dark energy's influence is relatively stronger than in dense regions. Gravity is pulling outward at the void boundary, while dark energy pushes the overall expansion forward. The result is a clean environment where the behavior of gravity on large scales can be tested with fewer complications than in the dense, dynamic environments of galaxy clusters. General relativity, Einstein's theory of gravity, makes specific predictions about how structures grow in an expanding universe. It predicts the rate at which matter falls together under gravity as a function of cosmic time, the relationship between the growth of structure and the expansion rate, and the way voids should expand as their boundaries drain matter. Competing theories of gravity alternative frameworks proposed to explain cosmic acceleration without dark energy make different predictions for all of these quantities. Measuring void statistics carefully tests these predictions. The abundance of voids of different sizes, their shapes, their internal density profiles, and the velocity patterns of galaxies near their boundaries all carry information about the growth rate of structure. If gravity behaves differently at large scales, then general relativity predicts weaker or stronger than expected, given the matter distribution. Void statistics will reflect that difference. The shape of voids is particularly sensitive to modified gravity. In standard cosmology, voids are predicted to be slightly elongated along the line of sight due to the way galaxy peculiar velocities, their motions relative to the overall expansion, are mapped in redshift surveys. This effect, called the Alcock-Paczynski effect, depends on the geometry of the universe and the growth rate of structure simultaneously. Measuring the apparent shapes of stacked voids provides a joint constraint on both quantities. Several analyses, using the Sloan Digital Sky Survey data, have measured void statistics consistent with general relativity and the standard cosmological model. Future surveys with Euclid and the Vera Rubin Observatory will extend these measurements to higher redshifts and much larger void samples, significantly improving the precision. Voids also interact with the cosmic microwave background through the integrated Sachs-Wolf effect mentioned earlier. In a universe driven by a cosmological constant, photons crossing a large void gain a small amount of energy as the void's gravitational potential becomes shallower during the crossing, an effect that produces a faint temperature increase in the microwave background in the direction of known voids. In some modified gravity theories, this signal is predicted to differ from the standard expectation. Cross-correlating void catalogs with microwave background temperature maps probes gravity at the largest accessible scales. The internal structure of voids also reveals information about the nature of dark matter. Dwarf galaxies found inside voids show properties that have sometimes been cited as in tension with the simplest version of cold dark matter theory, which predicts more small dark matter halos than are observed hosting visible galaxies. Whether void galaxies reflect a true deficit of small dark matter halos, or simply a deficit of conditions favorable to galaxy formation in halos that do exist, is an active research question. Voids are the universe's most expansive quiet zones, and they amplify the signals that dense environments tend to obscure. Testing gravity inside them is testing the framework that holds the entire cosmic web together. And beyond the edges of individual voids, where the largest filaments of the web pull matter into the densest concentrations, the universe reveals what happens when all of that accumulated mass finally comes to a point. Every photon of the cosmic microwave background that passes through a galaxy cluster is changed by the experience. The hot electrons in the cluster gas scatter those photons, boosting their energy slightly. The result is a faint distortion in the microwave background in the direction of the cluster, a decrease in brightness at lower frequencies and an increase at higher frequencies, with a specific spectral signature that distinguishes it from any other effect. This is the Sunyaev-Zeldovich effect, named for the two physicists who predicted it in 1970. It is well established, has been observed in thousands of galaxy clusters, and has become a primary method for discovering clusters and measuring their masses across the observable universe. What makes it particularly powerful for intergalactic science is that it does not depend on a cluster's distance in the same way that direct light detection does. A cluster at 10 billion light-years produces roughly the same Sunyaev-Zeldovich signal as an identical cluster at 1 billion light-years, because the effect depends on the total amount of hot gas along the line of sight, not on how bright the cluster appears at a given distance. This makes it a uniquely effective tool for finding massive clusters in the early universe, where optical surveys struggle to detect the faint galaxy light. The South Pole Telescope and the Atacama Cosmology Telescope have used this effect to conduct surveys of the sky for galaxy clusters, finding thousands of new clusters at distances corresponding to the first half of the universe's history. The cluster catalogues produced by these surveys have been used to measure how quickly the most massive structures in the universe grew over cosmic time, directly testing the influence of dark energy on structure formation. The thermal Sunyaev-Zeldovich effect has an intergalactic application beyond cluster finding. It can also detect the hot gas in the filaments connecting clusters, the warm-hot intergalactic medium described earlier. The signal from filaments is far fainter than from clusters because the gas is less dense and spread over a much larger volume. Detecting it requires stacking many filament regions and extracting a statistical signal from the noise. This is exactly the approach used by several teams to confirm the warm-hot intergalactic medium detection. By identifying pairs of galaxy clusters expected to be connected by filaments based on their proximity in three-dimensional space, and then stacking the microwave background signal from the region between each pair, researchers extracted a faint but consistent Sunyaev-Zeldovich signal from the intergalactic gas. The result was independent confirmation of the hot filamentary gas, using a completely different physical mechanism from X-ray detection. There is a kinetic version of the Sunyaev-Zeldovich effect, distinct from the thermal version. When galaxy clusters move relative to the cosmic microwave background, their motion imprints a faint temperature shift on the background photons they scatter. Measuring this shift for many clusters simultaneously allows reconstruction of the large-scale velocity field, how clusters and the matter around them are moving across hundreds of millions of light-years. This velocity field reflects the growth of structure driven by gravity and is another independent test of dark energy and modified gravity theories. The cosmic microwave background is not just a static relic. It is an active surface against which the modern universe is continuously imprinting its structure, its temperature, and its motion. Every cluster, every filament, every void leaves a mark on the oldest light in the cosmos. Those marks, read together, are assembling a portrait of what lies between the galaxies, with more precision than any single telescope generation could have managed alone. The scientific tools that established everything described in this story, the cosmic web, the warm-hot intergalactic medium, baryon acoustic oscillations, fast radio bursts, cluster surveys were mostly built for broader purposes. The detailed, systematic mapping of the intergalactic medium as a primary science target is a goal of the next generation of facilities, now under construction or recently completed. The Square Kilometre Array is a radio telescope network being built across South Africa and Australia, with an effective collecting area far beyond any existing radio facility. When complete, it will have sensitivity to the intergalactic magnetic field across large fractions of the sky, mapping Faraday rotation from millions of background radio sources simultaneously. It will detect thousands of fast radio bursts per year, turning them from a handful of cosmological probes into a dense statistical survey of the intergalactic medium's ionization and turbulence structure. It will also attempt to directly image the 21-centimeter emission from neutral hydrogen during the epoch of reionization, mapping the patchy process by which the early intergalactic medium was cleared of neutral gas. The Athena X-ray Observatory, planned by the European Space Agency for launch in the early 2030s, is specifically designed to detect the warm-hot intergalactic medium in emission rather than relying on indirect statistical methods. Its large collecting area and high spectral resolution in X-rays will allow direct mapping of filament gas temperatures and densities, resolving the physical conditions in the cosmic web's bridges for the first time. This is the first major observatory explicitly targeting the intergalactic medium as a primary science goal. The Vera Rubin Observatory, beginning full survey operations in the mid-2020s, will map tens of billions of galaxies across the southern sky using weak gravitational lensing. Its measurements of how galaxy shapes are distorted by the intervening mass, both dark matter and ordinary matter, will reconstruct the three-dimensional matter distribution across billions of light-years, directly probing filament and void structure at precision far beyond current surveys. The Dark Energy Spectroscopic Instrument is already operating, collecting spectra of tens of millions of galaxies to map baryon acoustic oscillations and galaxy clustering across cosmic time. Its early results have already hinted at possible evolution in dark energy. Its full data release over the coming years will either confirm those hints or eliminate them, with profound implications for the Standard Model. James Webb continues to probe the intergalactic medium in the early universe, finding the faint galaxies that drove reionization, detecting the cold streams feeding early galaxy growth, and characterizing the chemical composition of gas at the boundaries of the first large-scale structures. What these facilities share is the capacity to test physics in the intergalactic medium physics that no laboratory on Earth can replicate. The magnetic field strengths, plasma temperatures, density scales, and gravitational regimes in intergalactic space exist nowhere else. Measuring them constrains theories of gravity, dark matter, dark energy, and cosmology in ways that galaxy-scale observations cannot. The intergalactic medium is the largest laboratory in existence. It runs experiments at energies and scales beyond anything humans can build. For most of astronomical history, we have been reading its outputs with inadequate instruments. The instruments being built now will finally match the scale of the question. What those instruments find over the next decade will determine whether the Standard Model stands, is refined, or requires replacement. There is a number in cosmology that carries particular significance: roughly 300 million light-years. Below that scale, the universe is rich with structure filaments, clusters, voids, walls, all the complex architecture of the cosmic web. Above that scale, the universe is expected to become statistically uniform. Every large enough region should look like every other large enough region. The universe, at the largest scales, should be isotropic and homogeneous. This prediction is called the cosmological principle, and it is a foundational assumption of the Standard Model. Every major equation used to describe the universe's evolution depends on it. The cosmic microwave background, as measured from our location in the Milky Way, shows near-perfect uniformity in temperature across the sky, a direct confirmation of isotropy at the largest observable scale. But observations at intermediate scales, hundreds of millions to several billion light-years, have repeatedly found structures and alignments that push at the boundary of what the cosmological principle comfortably accommodates. The Hercules Corona Borealis Great Wall, if confirmed, is the most extreme example. Others include statistical anisotropies in the distribution of certain galaxy types at billion light-year scales, alignments in the polarization directions of quasars across large regions of sky, and the persistent cold spot anomaly in the microwave background. Each individual anomaly, considered in isolation, might represent a statistical fluctuation, a rare but possible outcome of an otherwise uniform universe. The concern arises from their accumulation. Multiple independent features, found in different datasets using different methods, pointing towards structure at scales that should be featureless, raises a question about whether the cosmological principle is as well tested at intermediate scales as it is assumed to be. The challenge in addressing this question is the sample size problem. We observe the universe from one location. We have access to one realization of cosmic history, not an ensemble of universes that we can compare. Statistical tests of homogeneity and isotropy are applied to a single sample, which limits how confidently any individual anomaly can be interpreted. Future large-scale surveys covering wider areas and deeper distances will help. If the current anomalies are statistical flukes, they should shrink in significance as surveys add more data. If they are real physical features, they should grow more significant or reveal additional structure that supports them. There is also the possibility that some anomalies reflect local effects rather than truly large-scale structure. The Great Attractor, a known concentration of mass roughly 250 million light-years away, toward which our local group of galaxies is falling, illustrates how local gravitational influences can produce apparent asymmetries in observations that must be carefully corrected for. Testing the cosmological principle at the scales where it is most relevant requires the very surveys now being built. The scale problem is not a crisis in cosmology, but it is an open question sitting directly at the center of the framework that everything else depends on. How uniformly the universe is actually distributed at large scales is a measurement that has not yet been made with the precision the question deserves. And the answer, when it arrives, will come primarily from reading the distribution of matter in and between galaxies from the same intergalactic medium that has quietly held the majority of the universe's ordinary matter all along. Everything discussed across this story, the filaments, the voids, the warm-hot intergalactic medium, the dark matter backbone, the baryon acoustic oscillations, connects to a single overarching picture of how the universe is organized, from the smallest galaxy scales to the largest observable distances. The largest confirmed structures in the universe are superclusters, concentrations of galaxy clusters, and the filaments connecting them, spanning hundreds of millions of light-years. The Laniakea supercluster, our own cosmic neighborhood, was formally defined in 2014 using a kinematic approach, mapping the velocity flows of tens of thousands of galaxies to identify the volume of space whose matter flows toward a common gravitational basin. Laniakea spans roughly 520 million light-years and contains the mass of roughly 100 million billion stars. Our own galaxy sits near the outer edge of Laniakea, in a relatively sparse region, flowing toward the dense core of the supercluster, along with thousands of other galaxies. Laniakea itself is falling toward an even larger concentration, the Shapley supercluster, the most massive structure in the nearby universe. The gravitational pull of Shapley influences galaxy motions across hundreds of millions of light-years. At the scale above superclusters, the cosmological principle should apply. The structures should fade into statistical background, but the mapping of superclusters and filaments up to that scale has revealed that even Laniakea is one node in a larger filamentary network. The Perseus-Pisces supercluster chain, the Centaurus supercluster, the Coma supercluster, all are part of the same web-like architecture, connected by filaments and separated by voids at scales that are only now being fully mapped. The transition from structured web to statistically uniform background is not a sharp boundary. It is a gradual smoothing, detectable only through statistical analysis of galaxy distributions over large survey volumes. Exactly where the universe becomes homogeneous, and whether it becomes homogeneous cleanly at the expected scale, is a live observational question. Contextualizing all of this within the full observable universe. The observable universe extends roughly 46 billion light-years in every direction from us. The cosmic web fills all of it. The warm-hot intergalactic medium threads all of it. The dark matter backbone supports all of it. Every photon from every distant galaxy has passed through the intergalactic medium to reach us. The sheer scale of what lies between the galaxies, not empty, not uniform, not passive, is the fundamental discovery of modern observational cosmology. Galaxies are islands. The ocean between them is structured, heated, magnetized, trafficked by wandering stars and high-energy particles, and encoded with the history of everything the universe has done since the first second after the Big Bang. Understanding what lies between galaxies is not a secondary topic in astronomy. It is the primary architecture of everything. And the most important implication of that architecture involves what it tells us about where the universe is going from here, what its future holds, written in the pattern of its expanding filaments and growing voids. The cosmic web is not static. It is still evolving, right now, and the direction of its evolution is determined by the competition between gravity and dark energy that has been building throughout this entire story. Understanding the current state of the web means understanding what comes next. In the early universe, gravity dominated. Matter was denser. Dark energy's influence was relatively weaker, and structure grew rapidly. The first filaments formed, thickened, and fed matter into the first clusters. The cosmic web assembled itself from the chaos of the early universe into the organized architecture visible today across billions of light years. Over the past several billion years, that growth has been slowing. Dark energy has strengthened its influence as the universe expanded and matter density dropped. Filaments are still transporting gas, mergers are still happening, clusters are still growing, but the rate of all of these processes is declining. The cosmic web is gradually running out of new material to recruit from the voids. Projecting into the far future, based on the current cosmological constant model of dark energy, the trajectory is toward increasing isolation. The universe's expansion accelerates. Galaxy clusters and their immediate surroundings, structures bound tightly enough by their own gravity to resist the expansion, will remain intact. But the filaments connecting those clusters will thin and eventually dissolve as the expansion pulls their distant ends apart faster than gravity can hold them together. The cosmic web will fray. On timescales far longer than the current age of the universe, the gravitationally bound structures that survive the superclusters of today will merge into single massive islands in an increasingly dark and empty, expanding universe. The distances between those islands will grow at accelerating rates. Light from one island will take longer and longer to reach the next, eventually redshifting beyond any detector's ability to catch. The observable universe, accessible to observers in those future islands, will shrink as distant regions accelerate beyond the cosmological horizon. The warm, hot, intergalactic medium that today holds the majority of the universe's ordinary matter in the filaments will gradually be disrupted as filaments thin. The gas will be pulled into the forming super-island structures or left behind in the expanding voids, too diffuse to observe. The magnetic fields threading the intergalactic medium will weaken as the universe stretches. This is the long-term prediction from dark energy as currently understood. The caveat is that dark energy's behavior in the very long future is genuinely unknown. If it evolves, if it strengthens over time, as some alternative dark energy models suggest, the timeline accelerates. If it weakens, the expansion could slow, and gravity might eventually pull the universe back into a collapse. The dark energy spectroscopic instruments' hints of possible dark energy evolution make this not purely a theoretical question. What we are observing today, in mapping the cosmic web and the intergalactic medium, is the universe near the peak of its structural complexity, the moment when the web is most fully assembled, most richly populated with gas and galaxies and filaments, before the long, slow disassembly driven by dark energy. Future generations of astronomers, if there are any, will inherit a simpler, emptier universe. The web they see will be fainter, the filaments thinner, the voids wider. We are observing at the right moment. The universe is showing us its full structure before dark energy begins to take it apart. Everything we have covered across this story, the warm, hot filaments, the rogue stars, the magnetic fields, the rogue black holes, the cosmic voids, the baryon acoustic oscillations, the reionization of the universe, the fast radio bursts, the Hubble tension, all of it connects to a single insight that reframes the entire picture of what the universe is and where its information is stored. The universe's ordinary matter does not live primarily in galaxies. More than half of it lives in the spaces between them, in superheated filaments barely visible to the best telescopes ever built, spread across structures that dwarf any individual galaxy by a factor of millions. Galaxies are not the universe. Galaxies are the bright spots in a far larger structure that we are only now developing instruments sensitive enough to read. This reframing has consequences. When we ask what the universe is made of, the answer requires accounting for the intergalactic medium. When we ask where cosmic history is recorded, the answer includes the chemical signatures of the filaments and the thermal memory of reionization encoded in the Lyman alpha forest. When we ask what shapes galaxy evolution, the answer points back to the filaments that delivered gas and the voids that isolated certain galaxies from the full drama of the cosmic web. The fundamental open questions in cosmology, the Hubble tension, the nature of dark energy, the identity of dark matter, the origin of intergalactic magnetic fields, the full history of reionization, the validity of the cosmological principle at the largest scales are all being tested primarily through observations of large-scale structure and the intergalactic medium. The between-galaxy environment is where the answers are hidden. There is also a philosophical dimension that the science itself supports. The universe, at every scale we have managed to examine, has turned out to be more structured, more inhabited, and more interconnected than the previous generation of science assumed. The voids between galaxies, once taken as evidence of emptiness, turned out to contain most of the ordinary matter. The darkness between stars contains rogue planets and hypervelocity stars. The magnetic field of the intergalactic medium may carry the oldest surviving relic of the universe's first moments. Every apparent emptiness has turned out to be a filled space with structure we lacked the instruments to see. The lesson is not philosophical in the soft sense. It is methodological. The gaps in our knowledge are not absences of interesting physics. They are exactly the places where the most important physics is waiting. The intergalactic medium was ignored for most of observational astronomy's history because the galaxies were bright and the space between them was not. The moment telescopes became sensitive enough to look at the darkness more carefully, the darkness revealed that it was the majority of what we were supposed to be studying all along. The square kilometer array, Athena, Euclid, Vera Rubin, the Roman Space Telescope, the next generation of fast radio burst detectors. All of these are looking at the same thing from different angles. They are trying to read what the space between galaxies is actually made of, how it got that way, and what it tells us about the rules the universe runs on. The between-galaxy environment is not background, it is the primary text. The galaxies are the annotations, and we are only a few pages into reading what that text actually says.